Okay. Okay. Oh, thank you. So I would like to talk about excess energy generation using a nano-sized multilayer metal composite and hydrogen gas. Oops. Okay. This is a background of and motivation of my study, of my presentation. I was involved in the research of permeation-induced transmutation with nano-sized multilayer thin film when I was a researcher of Mitsubishi Heavy Industries. We use this kind of palladium calcium oxide multilayer thin film and put the cesium on top, and we make the deuterium gas permeation like this, and we observe the transmutation reaction of cesium into praseodymium like this. In this study, key factors in this study are diffusion and nano-sized multilayer thin film, and also elemental analysis. And after moving to Tohoku University, I had a chance to participate in the national project, Japanese national project, NEDO project, and at that time we observed excess heat, anomalous excess heat with nano-sized metal composite particles. So in this case, key factors are nano-sized particles and hydrogen or deuterium diffusion and heat estimation were key factors. And combining these factors, we developed a new experiment to study excess energy generation with nano-sized multilayer metal composite of hydrogen gas like this. And using this new method, larger excess energy per hydrogen obtained. Okay. Oh. Okay. This figure shows the experimental method of the present method. We use nano-sized multilayer metal composite like this. Usually, mainly, we use a nickel bulk, 25 millimeter and 25 millimeter and 0.1 thickness nickel bulk. And on the bulk, we fabricate multilayer thin films, mainly using nickel and copper and other materials on it. And we prepare 2 sheets of this multilayer composite. And in the center, we have a ceramic heater to heat up this nano-sized multilayer metal composite. And we trigger the reaction using this heater. And this module is located in the center of the vacuum chamber here. And in the vacuum chamber, to estimate the temperature, we have some copper in here, in ceramic heater, incorporated in the ceramic heater. And also, we measure the surface temperature by infrared radiation thermometer like this. And we also measure the gamma ray emission using this NAI scintillation detector, mainly for safety reasons. We did not any increase of gamma rays during the experiment. Okay, so this is a procedure of this experiment is here. At first, introduce a sample, fabricated sample into the chamber. And about 1 or 2 days, we bake the samples to remove the mainly water or other impurities. And after that, we introduce a hydrogen gas into the chamber. And at the hydrogen gas temperature of the hydrogen gas introduction is about 250 degrees, and the pressure is 230 Pascal. And about one night, hydrogen absorption ended. And after that, we evacuate the hydrogen gas and simultaneously heat up the sample up to 500 degrees or 700 degrees. And we observe the excess energy generation by this triggering. And usually, half day after, we cut off. Heater is cut off and cool down the samples. And again, we introduce hydrogen gas into the vacuum chamber again, and repeat this process again. Changing the condition, input conditions mainly. Okay. So this figure shows the diffusion of hydrogen through the nano-sized multilayer metal composite in the present experiment. We assume that diffusion of hydrogen is one of the key factors to induce condensed matter nuclear reactions. So this is the cross-section of multilayer metal composite. Hydrogen in the composite behaves like this. Usually, hydrogen hopping from a side to another side like this. This process is known as quantum diffusion. And diffusion of hydrogen is caused by mainly a gradient of concentration of hydrogen. In this case, we have much hydrogen here, and if we pump up the surface, gradient of concentration of hydrogen is like this. And also, thermal gradient is also important for diffusion of hydrogen. This hydrogen diffusion is governed by this equation. Okay, this is a photograph of copper-nickel multilayer thin film and the experimental setup. This is an image of STEM, scanning transmission electron microscope image. You can see that the copper and the nickel are fabricated like this. Okay, and we have a chamber, about the 10-liter chamber, vacuum chamber. And also we have a radiation thermometer, and gamma ray detector is located like this. Okay. Before experiment, we perform blank run for calibration. Exactly the same process with bulk, nickel bulk. Instead of multilayer, nickel bulk, we perform the blank run, and we get this kind of a calibration curve. For example, if we input 10 watt to the samples, we get about 600 degrees, and if we input 20 watt, about 800 degrees centigrade. Okay. This graph shows the excess heat evaluation. During the experiment, we pumped up the hydrogen gas. So we should consider heat conduction and thermal radiation, only two terms. Heat conduction from the nanomaterial composite to the vacuum chamber, and heat radiation, thermal radiation from the surface of the sample to the chamber, okay? And these two these are equal into input power and excess energy, if we have. Okay. And as a first step, we assume that the emissivity for the thermal radiation is the same for nickel bulk and nickel-based multilayer thin film. The second step, we will estimate the emissivity will be by radiation thermometer detector. Okay, so I will show you 4 examples as an excess heat generation case. This one is the first one. In this case, we use 3 layers of copper size at 2 nanometer and nickel 14 nanometer, combined 3 layers on the nickel bulk. And at this point, we start hydrogen absorption here. As you can see, this axis means the pressure. Blue is the pressure, and the red is excess power. As you can see, pressure goes down, so this sample absorbed hydrogen like this. And at this point, we evacuate the hydrogen gas in the vacuum chamber, and simultaneously, heater switch it on, and about 8 degrees centigrade, 850 degrees centigrade, we heat up the samples. Then we can observe the excess power about 3 watt, like this. And after that, at about a half day, we switched off the heater, and also we hydrogen absorption again at this point. And next morning, changing the input power, we perform the same experiment. About 600 degrees, we get 1.2 excess power. And after that, if we input about 25 watt, about 970 degrees centigrade, we get 3 watt of excess power. And we repeat this process, and we check the reproducibility for this experiment. Okay. Next one. We change the sample. And the other processes are all the same. If we use 6 layers, copper and nickel 6 layers, we got much excess power like this, as you can see. If you compare, oops. In the case of 3 layers, we can see about the maximum excess power about the 3 watt. But if we use the 6 layers of copper nickel, we can get 5 or 5.3 watt or more larger excess power we get. And also trend of the excess heat is different. In this case, excess heat tends to increase like this. Okay. Okay, I will show you next example. Example 3. Example 3. Wow. Example. Okay. Example 3 is a result using 6 layers of copper nickel with calcium oxide. A little bit complicated sample. We put calcium oxide into the nickel like this. Nickel, originally nickel 14 nanometer. So 7 nanometer nickel, we have 2 nanometer calcium oxide like this. If we fabricate like this, we get excess heat like this. You can see that nearly almost similar excess heat we got, but the trend of the excess is different because in the case of no calcium oxide, excess heat seems stable, but if we input the calcium oxide, excess heat goes down like this. And also, absorption rate is a little bit down. And next one is 6 layers of copper and nickel with Y2O3. Y2O3. In this case, excess heat is less than calcium oxide. And if we summarize these 4 examples, this figure shows the temperature dependence for 4 samples. Blue is 3 layers, and red is 6 layers, and green is 6 layers with calcium oxide, and this one is 6 layers with Y2O3. So you can see that in the case of Y2O3 sample, takes a peak about 750 degrees centigrade about. And also, we can see that these curve like a convex shape. So these curves are not dependent on temperature to force. So it suggests that these effect, not the artifact, by the effect of by thermal radiation. So, okay. And if we estimate the released energy, released excess energy per hydrogen, we can show you here. This is the 3-layer, 6-layer calcium oxide and Y2O3. We can see that the absorbed number of hydrogen is here, about almost all the same, but larger for the normal layer. But excess energy per hydrogen is here. In this case, 6.3 kilo eV and 16 kilo eV, very large. So usually chemical reactions release at most 1 electron volt per hydrogen. So in this case, kilovolt order. So it strongly suggests that non-chemical nuclear reactions occur in this composite. And if we consider, if we postulate that nuclear reactions ranges about 1 mega electron volt or 10 mega electron volt order, about 10 to minus third of hydrogen involved, absorbed in this condensed matter, react. Okay. This is a view graph for simultaneous detection of heat bursts. In this case, the red line means heat temperature, and the blue line surface temperature by thermal radiation thermometer. As you can see, at this point, heat burst phenomena occur, and simultaneously surface temperature go up. And during this experiment, we check the input power and the room temperature. These are very constant, so this increase is a heat burst, I think. And more important is temperature increase was confirmed by 2 independent, by thermocouple and radiation thermometer. Okay, so we would like to know that reaction mechanism. So we would like to know what is happening in the composite, small composite, metal composite. So we apply the samples before experiment and after experiment. We apply SEM-EDX and the ICP mass and the TOF SIMS and the Q mass and XPS and TEM and the STEM for the samples and investigate what is happening in nano-sized multilayer metal composite. And we would like to obtain key factors to control condensed matter nuclear reactions. So, and I will show you an example of experimental analytical analyzed result. This is a Blank-Run sample. After Blank-Run sample by SEM-EDX analyzed, we can see the surface of the nickel, and by EDX, we can see the carbon and oxide and, of course, nickel. Almost all the nickel, but contamination of carbon and oxygen is here. According to the mill sheet, nickel plate you have silicon and manganese and mangan like this. Now, this figure shows the change of surface by SEM-EDX. This one is analyzed data for the 6 multilayer data. As I show, a very good one, a large excess heat sample. Before heat generation, we do not other material, usually nickel and carbon and oxide. In this case, we fabricate the copper, but by the EDX analysis, copper is very small amount, so we cannot detect the copper in this place. But after heat generation, it depends on the place, but in this place, in this point, we have lot of elements like this. Copper and zirconium, sodium and magnesium, aluminum and potassium, like this. Okay. But apparently, different change is different, changing. Surface is changing, but very difficult to understand or analyze based on these SEM-EDX data only. So, because these are very abundant elements, so discrimination of products and contamination is very, very difficult. So, I'll show you another data. For the same sample, after the heat generation, we can, if we use Topsham's surface distribution is here. This is the sample surface, and the surface distribution of sodium and calcium and potassium and titanium and manganese and iron here. You can see that the calcium spot is here and corresponding to sodium, and also we can see titanium and sodium correspond. And very strange, manganese and iron distribution is reversibly. So it is very strange, but very difficult to analyze what is happening. But it is necessary to get surface analyzed data. Okay, I will show you another information about depth profile by Topsham's. It is a case of Y203 case. Depth profile, it is the surface of the sample, and about here, nickel region here. So we can see this one is a nickel, yttrium, copper, and iron, and polonium, and manganese, and silicon. Based on yttrium profile, multilayer structure partially remained because this sample is at a very high temperature, so elements diffuse, so a little bit complicated, but partially remained as multilayer structure. And iron is here, and chromium is here. Usually, iron and chromium, which could be supposed to be derived from stainless steel by sputtering process, but distribution is greatly different. And also, we can notice that ratio of copper, nickel and copper on the surface is low, and many things. But in the case of silicon, it seems to be very reasonable distributed, because this silicon is an impurity, I think. Anyway, at this point, it is very difficult to conclude about elemental analysis. Anyway, further investigation will be processed, paying especially attention to the isotopic anomaly, since discrimination of contamination and reaction products is very important, I think. Okay, so I will mention about our division. Now, this one represents a present collaboration relationship. I am the member of Condensed Matter Nuclear Reaction Division, Tohoku University, and we mainly collaborate. This division is supported by Clean Planet, it's a venture company, and we still continue collaboration research with Mitsubishi Heavy Industry about transmutation experiments. And but this presentation is results of collaboration research with Clean Planet. And our division originally planned from 2015 to 2018. But recently, this condensed matter division extend to 2019 to 2022, more 4 years extension. Okay, so we'd like to conclude my presentation. A new type of excess heat experiments using a nano-sized metal multilayer composite and hydrogen gas have been performed based on the permeation-induced transmutation experiment with multilayer thin film and the excess heat experiment with nanoparticles. 2, excess energy generation using nano-sized multilayer copper-nickel metal composite and copper-nickel metal with solid material, for example, calcium oxide and Y2O3. Composite are presented as examples. Maximum released energy per absorbed total hydrogen was 16 kilo eV or 1.5 gigajoule per hydrogen mole. It strongly suggests that the observed heat generation must be of nuclear origin. And 4 years extension of condensed matter nuclear division of Tohoku University were approved. We would like to proceed to other realization of a new energy source. Thank you for attention. And acknowledgement. Thank you.
So thank you very much. Many questions. Dana Secom, here, please. Here, please.
Can I start?
Yeah, in front row. Someone who has not asked a question.
A short question, Mentai.
Two related questions. What do you think the actual reaction is?
In this case?
Yes.
Yeah, it's a very difficult question because I think many reactions occur in this case, so very complicated. So we should more simple. Make a more simple experiment, I think.
Okay, and related to that is, what do you think the role of copper is in the reaction? Yeah,
I think so. I suppose I suspected copper is playing a very important role. I think.
Now, Imam, please, over on the side.
Your input power is around 30 watt. Is it true?
Sorry?
Your input power.
Input power by DC supply, and what is that?
The amount of input power, 30.
About 10 watt and 20 watt and 27, 3 cases we. Okay.
Okay.
Okay, and the more interesting question is, you saturate in the, you put hydrogen pressure very low, like 2 millibar.
Yes.
First, why? And then did you try high pressures? Because one could expect.
That's a reasonable question. We tried sometimes more high pressure, but absorption is not so changed, was not so changed. So we fixed to 130 Pascal. So it is necessary to further investigation, I think.
Okay.
And can you estimate the loading ratio in this case? Of? Yeah.
How?
Loading ratio.
Loading ratio, yeah. It's also very, in this case, about 0.003 or something like that. Usually, nickel do not absorb so much hydrogen. So, in the case of nickel, or about these temperature area, 10 to 4th. But in our case, about here, more larger, but 10 to 3rd. Okay.
Imam.
Yeah. Copper and nickel is an isomorphous alloy. They will make isomorphous material. Their alloying is going on.
Yeah, that's
So-
right.
so-
Alloy is going on.
Yeah.
Copper, nickel, so that's
So
right.
interface is changing.
Yes.
You have initially you have
Yeah.
less alloy, then you have more alloy, then you
Yeah.
have more alloy.
Yeah.
And the temperature shows
Yes.
that you may have completely alloy, not any more copper and nickel.
Yeah.
Maybe very little left.
Yeah. So it's a very complicated process. So we should simplify.
Yeah, Emmanuel.
Yeah, here. And a question, do you have access to X-ray diffraction analysis facility? Can you perform X-ray diffraction experiments on the material before and after?
What kind of?
X-ray diffraction analysis.
X-ray diffraction. X-ray diffraction. Yeah, sometimes we did.
Okay.
Sometimes we did, yeah.
Did you find some interesting
Yes.
intermetallics compound? Because maybe
Yeah.
you can have diffusion, so
yes,
at high
that's
temperature. So.
We performed X-ray and diffraction, and we detected many interesting things, but it's very difficult to present. So we should do more measurement by XRD. Okay.
So Matthew, and would you bring a microphone to the front row, please? Matthew.
In your presentation, you are showing the scanning transmission electron microscope. Have you done some diffraction pattern analysis of that sample to be evaluate to evaluate the structure, the metallic structure at the interface and the amorphous deposition you've been doing with copper?
So we found many interesting things, but at this point, it is very difficult to solid conclusions. So that
Two more questions, please. Chelani?
Comparison between calcium oxide and yttrium oxide, the main difference is the low working tension calcium better than yttrium. So it means the role of electrons, that you was a pioneer and we follow a lot. Some further comments?
Thank you.
Thank you. You got some excess heat for some time. How long, what is the longest period you obtain excess heat in your
Duration of excess heat, usually half day, but 2 weeks. We have experienced 2 weeks excess. Of course, excess heat decrease, but still about the 1 watt or something like that. Okay.
Maybe so I have another question, because you have so many thin layers, you get at this high temperature a complete diffusion
Yeah.
of nickel and copper,
Yeah.
and you even show this diagram with thickness 140 nanometers, where you see a flat distribution of nickel and copper. So you get a uniform ingot of copper nickel, of course, tantalum.
Yes, I try to make a constant experiment.